Oh, you think so? But you have chocolate muffins.
No, it's not chocolate. It's tea.
No, your food, chocolate muffins.
I have to buy my own money, not my mom money.
This is all I have.
Because maybe you not save money.
Oh, I save money.
Yeah, me too.
Too much savings. This is the problem. Okay, you can help me. Can you change the focus?
No, just spin.
Yeah. Oh, yeah.
Yes.
Yes. Oh, no. What? Yeah.
The other way.
Turn. Yeah. Yeah, and maybe to the right a little bit. Careful. Yeah.
That's it.
Yeah.
And with
No, not down. There, that's fine. That's fine.
Yeah, that's it. That's alright.
because of the wire.
It's a wire, isn't it?
Yeah.
I got it. There. It'll do. Right. So have you got the data for this question? Yeah. How's the mechanics revision?
It's really going good.
Gone good for you?
For me.
For you? Gone bad? What did you revise last?
Like 3%. Now I'm like really.
3%.
Yeah. And the cantilever and this thing like.
Now, do you understand why now I say I'm confused why students find it so hard?
No, if you do it like 2 to 3 times, then like you'll.
Yeah.
Focus.
Yes. But do you understand when I said I don't know why students find this so hard?
It's hard.
But is it hard?
No, like
You see?
it's hard for the first time.
Yeah. It's hard the first time. And maybe the second time.
And
Then it's easy the
yeah.
third time.
And
No,
one more thing.
because,
Why all the questions like from first to 3 they are easy. The last one is also like killing.
It's to challenge you.
No, because some people like first, second time it will be hard. Third time it will be hard.
Thank you.
But some people might find 1, 2, 3 too easy and they want a hard one.
Maybe.
I'm
One
one
is
of
the
those.
hard.
Yeah, I said some people. Yeah. I didn't say who. Yeah. Alright. What's our data? So we have oh yeah, well they'll call it out. They'll make themselves useful. Yeah. So what's the V? Is it V and I, yeah?
Yes.
Oh look.
Well, PD and I.
Potential difference.
Oh, you got it.
Yes. She did her homework in Excel. She didn't want to draw me a graph. That's okay. So it goes 1.625 all the way down to 0.625. Yeah, and the current starts at 0.5 and then goes up until 2.75. Fantastic. Right, so what is the first question? Draw a graph. All right. Thank you. So did you draw the graph or did you use Excel like me? Good. Right, so homework. X-axis PD in volts and then current in amps. There we go. Right, so what's the first question then after drawing? Oh, thank you. Graph. B. What's the internal resistance? Right, I'll be very bad and lazy and just have Excel calculate it for me. I know, so lazy. Show equation. There you go. So the internal resistance is 2. Well, just be careful what I'm... Yes?
Yeah.
R, M is minus R.
Yeah, M is minus R, so R is minus M,
Yeah.
which is minus 2, which is 2. Did you say -2?
M.
Is -2, yes. Right, what's this next part? What's the EMF? Your graph is upside down. Did you put volts here?
Well, no.
See, I knew that. I knew that. Alright, what's the next one? The EMF. EMF will equal 4. Again, because it's +4. What did you say?
I don't know.
No. No formulas for EMF. Guys, remember what the EMF is on the graph?
See.
Yeah, it's where it crosses the axis. That's the EMF. Do you remember this? I don't know, is that yes or no?
Why it's not the highest point?
Because... oh, my heart.
Couldn't touch the wire.
I think we talked about this last time too, didn't we?
I didn't get it the last time.
We should have, okay. We have to draw this line until we hit the y-axis. Now, you can't quite see it on my graph, but the y-axis is, look, 0.8, 0.6, 0.4, the next one, 0.2. Yeah, you can't quite see it because my graph isn't... I wonder, can I edit... Oh yeah, maybe I can change the data ranges. I'm going to...
But in the exam, how are you?
No, hang on.
Good question. That's a good question.
But in the exam you wouldn't draw it like this. On the exam you would draw it all the way to the x and the y axis. You know what I mean?
On the graph paper.
On the graph paper, yeah. I just need to shrink this down.
So you know what the last line is.
Yeah. Oh, come on.
Is this the only graph where you draw the potential difference in the x?
Hang on. I'm having a problem. Move. There we go. Finally. Right, now I'm going to fake it a little bit. So in real life you can draw the graph whatever way you want, but I'm going to need to fake it a bit here. Yeah. So, Mishri, this is what you do in real life. In real life, you would draw this on your graph, but then you would continue the line back on your graph paper until it hits the y-axis. And where it hits the y-axis is the EMF. Yeah. So this is 4. Is that okay now?
Yes.
Why
Is it-
not use the formula?
What formula?
The
Which-
EMF minus V minus IR.
Well, I suppose if you know the or, you could use the formula. What was the formula I gave you last time? EMF equals
I or
V.
or Z.
V
plus
I
IR.
smaller.
V plus IR.
V plus I or. Yes. Okay, well, I suppose now that we know that this is 2, we could use it. You'll have to pick a voltage. So let's pick an easy voltage. 1. So when the voltage is 1, what's the current?
2.
2.
So it
Two.
will be 5.
Yeah. What?
No, that's not right. There might be... Is this the right formula? Is this what I gave you last time?
Yeah.
Because V is equal to IR and then
Yeah, it's right.
V equals.
Yeah.
Yeah.
Show me.
Yeah, EMF equals V plus I smaller.
Oh, I see. Interesting. This is the formula I gave you last time. I said Well, it's the same formula here. V equals minus RI plus EMF. So that means V plus RI equals EMF. V is 1, R is 2, I is
2. 2.
2.
So it's 5.
Did I read this wrong? No, it is 4. My goodness, what's going wrong here? I know this answer is right, so I don't know why this answer is wrong.
I is the 1.8 or 1.7? No.
Well, I used V is 1 and I is 2 in the table. Something's very strange here. Something's very wrong. Something ain't right.
I is 2.
Is it not? When V is 1, I'm looking at the table.
It's 1.5, is it?
No, when V is 1, I
When V is 1, I is 2. Okay.
Oh, hang on. I think my numbers here are wrong. 1.25, 1.5, 1.752. Oh no, that's okay. When V is 1, I is 2. Yeah. So what the heck? Now what's gone wrong? Yeah, wait a second. Did I plot this the right way? Are you sure I did? I think maybe Musharif was the only one who plotted it the right way. Do you put V here?
Yeah, because you did like this in the lecture.
Yeah, so it is 0.5.
Then it is. Thank you, Musharif. So I had it upside down.
Okay.
That's why. Ha ha ha. But does that mean everybody did it backwards as well?
No, I got the IV on the V is on the left, is on the Y, and the I is on.
So why didn't you correct me then?
Well.
You believed in me too
Yes.
much. Yes, you see,
Yeah.
this is the mistake. Right. Okay, let's try this again. Thank you, Musharif. I have one student brave enough to stand up to their teacher. Right. Scatter. Let's try this again. Homework. And on the x-axis, I, and the y-axis, V. Yeah.
So it's same like me.
Yeah, everything's great now.
Yes.
So, 0.5. And the EMF, 2. And if we use our formula, that should be right as well. EMF equals V plus IR. When the V is 1, for example, the I is 2. And the R is
2, 5.
0.5.
1 plus 1 is 2. Yeah.
Yeah, so the formula works. Thank you. Okay.
The R is 0.5.
Yeah, I was wrong. The R is 0.5. Because my graph was upside down.
But I use this.
No, your graph is wrong as well. Here should be I and this should be V. You made the same mistake I made. Yeah. Okay. Right, so it's all fine now, yeah? Right, the next part. Oh, I don't have it. What's asked for next?
Oh, graph and table of R, I think. Yeah.
Which number?
Part D now, is it?
D as in an extra row of load resistance.
Okay. Oh my goodness, come on. I'm just going to delete my graph. I hope I don't need it again. Right. Add in an extra row for resistance, yeah?
Yes.
Okay, so what's the formula for resistance? It's in ohms, of course.
Oh, yeah.
V...
V upon I.
V over I.
V over I.
Upon.
V over I, is it?
Yes.
V I R, yeah. So that would be this one divided by this one. So can you see how the resistance changes? Remember we said we had a variable resistor. Yeah, so what's the next part now?
Power.
Ah, right, so now we want power in watts. Yeah. So what's the formula for power?
IT.
IV, isn't it?
Yeah.
Okay, so down it goes. Right, what's the next part?
I think that was it.
No, there has to be more, is there? Well, no, was that it?
No, it's not time.
Yeah, I didn't think so. What else?
The
Graph power
power,
against
yes.
load resistance. So graph these two. Put the resistance on the X and the power on the Y. Did anybody graph this?
Yeah.
And what shape did you get?
Linear.
Did you? Are you sure? Is it linear? Let's have a look. Not too linear. Is this what you got?
Outside.
Really upside down? Well, we all make mistakes like that. That's okay. Right. Let's just put in smooth lines. Okay. Right. So this is my graph. Blah blah. On the x-axis is resistance in ohms, and on the y-axis is power in watts. Now this is a rather interesting graph. Oh, sorry, I'm missing the x-axis. Doesn't matter. The vertical lines. It's not linear. If you were to look at this graph, it increases and then decreases. So as you increase the resistance, you get more and more power, and then you get less power. Now I just really want to explain what's happening here. So remember we have our battery, and there's a cell inside of it, yes? And what else is inside of it? A small resistor. And then we have this going around a resistor here which we can change. Okay? Now, this is doing work. So it has a power here. And as this changes, we get different power coming out. So like for example, if the OR is 0 ohms, then how much power is it performing? 0 watts. So it starts off with 0 watts. And then if you increase the resistance, is it doing more or less work?
More.
It's doing more work. So if I increase it to say 0.5, it's doing about 2 watts. Now if I increase it again to 1, what's happened? It's doing about 1.7 watts. So this is interesting. If I put in a bigger and bigger resistor, it will increase, but then it will decrease. And what happens if I put in too big of a resistor? How much work will I get? If I put in a really big resistor, yeah, it gets smaller and smaller. Yeah, so it's going down to 0. This is an important concept. Who's doing electrical engineering? Yeah, this is something called load matching, I believe. So when you connect something to a battery,
The energy will like transfer.
I do not know what this means. Of course it transfers because it's a battery. Let me finish. When you connect a resistor to a battery to do some work, so this resistor could be a Game Boy, a toy, a laptop, whatever. If it's too big, you get less power. The best resistance level to use is one that is 0.5. But that's not a coincidence. 0.5, we saw that number earlier. What was that for? It was the small resistor. In other words, the best external resistor to use is the one that's the same size as the internal resistor. If your load is bigger than this, you're going to get less power. And if your load is smaller than this, you'll get less power as well. This kind of makes sense, because if you think about it, if I try to put my battery in your phone, it doesn't work.
Yes.
We have less power, not enough power, you know. And likewise, if I put if I put this battery in a really old phone, it will get less power as well. In other words, the best value to use is the same as the small or. And this is in electronic engineering called load matching. Now, you don't need to know that for the exam, but the reason I did this question is this, I don't have the question here, but this exact question, it was pretty much like this in the exam. So they ask you to make the normal graph, then they ask you to make OR, then they ask you to make P, and then they ask you to make a graph like this one with P and OR. And then the last question was, what is the maximum power? And you're supposed to realize that the maximum power is when the OR is also 0.5. So this is exactly a electricity exam question here. And it's a pretty nice question because there wasn't anything too difficult in it. The most difficult formula in it was the VIR triangle. The question was only a pain because you had to calculate everything. But it was just a straightforward calculation. Yeah. So if you wanted to read more about this, especially the people doing electronic engineering, you could Google something called load matching. This is what this phenomenon is here. Yeah. Okay, so we'll go on to the next lesson, and then.
So the answer is going down.
Basically, yeah. For
R is going 5.
Yeah. Yeah. And my point is, it will always be like this for these graphs that go like this at Musharif, that go up and then down here. What? Am I getting his name wrong or something? Next lesson.